All right, so today we are in chapter 5 of our discussion, and we will talk about two major subjects, multiplexing and compression. Now, from your reading of the chapter, what is multiplexing? How would you define multiplexing?
Multitasking.
Okay, multitasking. Okay, very good. Any, what would be the purpose of multiplexing?
Handle more than one signal at a time. Or
Yeah.
processing more than one thing at a time.
Very good. So it's all about sharing a specific medium. Okay, sharing the medium. So the idea is that it's very easy to do networking when I can plug in a wire to my workstation and whatever workstation I'm talking to. If we can have dedicated medium between us, then networking is fairly easy. At that point, all we have to do is just have to make sure that the wire its capacity is enough to whatever we're sending across. Well, building infrastructure is a little bit more difficult because when we communicate with the internet, we cannot have a wire go to every workstation out there in the world. What we see as a realistic scenario is that all our systems are going to connect to some magic device that then is going to send all our signal over a single wire. And then that single wire is going to go to a backbone of the internet, and then a single wire then will connect to a building and then to a workstation. Okay? So this ability to put together multiple signals onto one medium, that's where multiplexing comes along. So multiplexing, the first version that we want to talk about is the frequency division multiplexing. Frequency division multiplexing is really very simple. Consider the old style radio. Okay? The medium is what? When we talk about an old style radio, what is the medium of communication? Okay, but what's the medium? Airwaves. So the actual atmosphere, okay, is the shared medium. So the question was, how can we have multiple channels, okay, where we have the same air that we're sharing? And the answer was, well, how about if we have multiple frequencies? See, we share this medium, multiple frequencies, and then having multiple frequencies allows us to tune in to different stations. And this is a very effective way of sharing medium, to just dedicate certain frequencies. Now, when you do that, you have to have guard frequencies, because when frequencies of two channels, like a radio channels, come together, they'll tend to overlap, okay? And that causes problems with the transmission. So those guard frequencies go in between. And because of those guard frequencies, then there's large overhead of frequencies that are not actually being used. Okay, so that was always the downside of the frequency division multiplexing. Another area where this type of multiplexing is used is in cable television. So now we're not sharing the air, but we are sharing a single wire that comes to your house. The coax cable comes to your house, and in this cable there are multiple frequencies, and depending on which frequency you tune in on, that's the channel that you see. So that's a frequency division multiplexing. And so a pretty picture is on the screen here where we have multiple frequencies in between that special device, and the device is called the multiplexer. And on the other side, you can then divide the frequencies again by using demultiplexer, which is really the same device, only working the opposite way. So in the between, you see, we share the same medium. That's the whole idea, that we share the same medium. So frequency division multiplexing works okay for radio. It works okay for cable television. The more often used multiplexing technique is the time division. Now, time division is actually simpler, because in time division what we mean is, imagine trains trying to share the same track. Okay? One gets to go through, the other ones have to wait. Then another gate opens and the other one can go. And another gate opens, another one can go. So it's the same track and they have to share the time on that track. Okay? So time division requires that whatever messages we have, we're going to hold them until it's our time to use the shared medium. A very simple principle. You know, we use it in real life all the time. The effectiveness of this is quite nice, and in our operations here in the classroom, when you have the computers all connected to a switch in the cabling room, we use time division multiplexing. Okay, it happens very, very fast. Okay, but it has limitations. For example, as you connect more devices to the multiplexer, it's going to take a longer time for us to wait for our turn to take control over the media. The great thing about time multiplexing is that when you have your time, you can use the full throttle, the full bandwidth of whatever media we are sharing. So that's a great benefit of it. The synchronous style of time division says everybody in the classroom gets their slice of time, and even if you have nothing to say over the network, we still are going to pick up your empty data and send it along. So it's a very basic time sharing, and the overhead now is created by everybody that doesn't have anything to say, but they still get to fill in that card on the train. Okay? Because as the train moves along, we all get to fill in one card, and when you have nothing to say, that card goes empty. So now the upgrade, the upgrade to the synchronous time division would be to use what's called the asynchronous or statistical multiplexing. Let me see if I can get to a picture of that, where the picture is right here, so that when the computer is idle, you can see that computer B and D are idle, they have nothing to say, we simply do not include their slice of time in the communication. To do that, we simply had to add an address for every frame that's being sent out. So when A is sending data, we take the data piece and we add to it that A is sending it, and now C is sending it. So on the other end, we can send it in the right place. Before, the simplicity of the design was that everybody got to talk, and so the device on the other end didn't have to be intelligent, didn't have to say, is A talking, is B talking, because everybody had their slice and dedicated time. So this statistical or the asynchronous time division multiplexing allows us to save this shared media, the shared medium, to only use it for data that actually is intended for communication. Yes?
Is this the type of multiplexing that involves a clock? How is time calculated? Is it always constant, or is it always... How do you determine the slice of time?
Very good question. So this is where the intelligence of the multiplexer is going to decide whether this is a faster standard or a slower standard. There is a standard here called the SONET, as well as T1. Okay, and these all use time slicing, but with SONET, the time, there's only one clock. Therefore, the precision can be very high. In other approaches to this multiplexing, the time is spread across multiple clocks, and then synchronization needs to take place afterwards. Okay. So if you look at this first picture, when we simply send data from each one of them, okay, the data goes in specific sequence. So then the multiplexer has to sync to that sequence. Right, right. So they have to sync to the sequence, and that's how it can read it out correctly. So there's going to be error detection and correction in place, so the data can be resent if, in fact, there was noise on the line or something came out of sequence. But the great improvements in the clocking of it was done in the SONET type of a network, and the SONET can be used both with electrical or with fiber channel, okay, with light. But the great improvement was done to it so that the speed of the transmission can be very high, and that's primarily because of a single clock being used. So no space is wasted in the stream. It doesn't really show a nice comparison, but for now what we need to know about SONET is that it can be a very high throughput standard. And later on, when we talk about city level networking, we'll see that the SONET loops utilize this standard, and for a long time they've been a very effective way of connecting not just computers but entire campuses, because they can provide this high throughput multiplexing. So that's time division multiplexing, and the statistical time division multiplexing is this intelligent, is this upgraded way of doing it, so that even without changing the bandwidth of the connecting wire, we can continue to send more and more data through it. All right. This takes us to the wavelength division. And wavelength division multiplexing, it is in practice the same as the frequency division multiplexing. Okay? Wavelength division multiplexing is the new technology. So we tend to create new words and new terms when something new comes out. But wavelength and frequency are, of course, related. So we use wavelength when we use the expression for frequency multiplexing when we talk about radio waves, and we will talk about wavelength division when we talk about fiber channel and light transmission. Okay, but it's the same idea. Imagine two prisms. Okay, think about Pink Floyd cover for the Dark Side of the Moon. All right, two prisms with light coming in. And what you can do with a prism is you can have multicolored light, then turn into white light. All right? And so in between the medium that we're sharing is this white light, and that's what goes through our channel. But then on the ends, you see we can spread it across, and each of the wavelengths, the lambda, each of the wavelengths can carry its own channel, its own signal. So the zeros and ones, the flickering in the light would then be, the red light would be different than the green light and so forth. And so you can share that way the medium. Say it again? Time. So you still have to sync, you still have to have timing done, so that way things like when the data is sent, both have to be listening at the same time, right? But just like on a radio, even though you're tuned into the right radio station, the program comes on, you know, and you need to be there to listen to it. Now the wavelengths themselves are not actually the visible light. Okay, so for simplicity reasons, I use prisms and red and green. The light that's actually sent is not in the visible media. And there are multiple reasons for that. Some of them have to do with the properties, physical properties of the visible light, and that is it creates heat. And when that is sent over fiber itself, it can cause damage to the wire. But that's wavelength multiplexing, and it's the same principle. We have various wavelengths, and so now we're talking about the laser. Right, laser that would send different wavelengths, and then this is put through multiplexer, and the fiber optic line is that shared medium that we are attempting to share and to optimize as far as how much data we can send through. Very good. Let me switch here to an article on multiplexing, because there's a picture I want to show you. Okay, so this is just the general idea of multiplexing, where you have multiple workstations, often with slower lines, coming in to that special device that's going to multiplex, and then together we're able to combine these signals through a network. And so this picture right here, you see, it shows you the idea of time division multiplexing, where specific clients are connected on both ends, and they have a full use of whatever the bandwidth is on the connecting wire. And that's the general idea for time division. So some of the great improvements made to multiplexing have always been based on a need. And an obvious need, for example, at home for networking, was that the most common wire coming to home is the phone wire. So when you consider the top speeds that are physically possible on the phone wire for a voice signal, it's about 56K. Okay, so at 56K, we sort of maxed out what the analog transmission turned to digital could be. So some thinking was taking place to use a multiplexing device, but multiplexing in such a way so as to make the phone line carry more data at the same time. And what they figured out they can do is, instead of sending a single analog signal, right? You remember when you perhaps were dialing in to the internet in the time of modems and phone lines, you could actually hear the signal. So how about if on that phone line we don't send just a single audio signal, but we can use many different wavelengths all at the same time to communicate data, and then we put them together at the end. Okay, and this is where the DSL with a discrete multitone came along. The DSL, based on discrete the DMT, discrete multitone, allowed us to send multiple frequencies through the same wire. So the phone line was the limitation. We can send multiple signals and then multiplex them back to be the same workstation communication. And that's how the same wire, but now allows you to have the 6 megabits or even higher connectivity. So multiplexing is a very smart way of either sharing a media or optimizing whatever is there already in place.
So it's an audible tone, actually? Is it something that, you know what I mean? Can you actually hear it or no?
I don't think you can hear it, because if you recall, on every other phone line that you have, if you have DSL at home, if you had other phones, you had to put a filtering device on that. So I don't think there are sounds that you can hear, because it uses the multitone. So I don't think you can hear it, which is why there's a whole stream of them coming all at the same time. So yeah, to us it would be just noise probably, but it's the multiplexer that can pick up and then separate those so that you can put together frames that the computer can understand. But the bottom line is that using multiplexing allowed us to reuse these wires and provide a new way of communicating. So what you see here is multiple streams that are in the actual wire, and then we come out with whatever data was being sent and received. So this is sort of the opposite, right, of what we did before in terms of having multiple connections share a single wire. We use multiplexing here to actually optimize on how much data can end up in one household. Right, so there's again where the need created, or a different need created a use for multiplexing. So this brings us to yet another form of multiplexing, which is the code division. And this is not a new method. In fact, the military as well as the space program have been using that for a while. And the idea is that each device, instead of using a unique frequency, okay, each device has a code on it, which allows us to have a lot of different devices. And so now that the device has a code on it, it can use multiple frequencies, okay, and it's able to encrypt its communication quickly, and it can hop between frequencies. And those properties made the CDMA, which is the network used for voice, made it very useful for creating clear audio connections. Qualcomm was actually the company that took this idea from the military and applied it to consumer electronics. So that's the code division multiplexing. The code is a 64-bit code, so it's a very long, unique identifier that goes on the device. And then the opposite of the code is sent as a 1 versus a 0. So you actually are not sending zeros and ones, because if that was the case, it would be easy to pick it up and eavesdrop. So instead, your code actually determines what a 1 is and then what a 0 is. And that's how we can then share, again, the same medium and send and receive data that is readable only by us. So here an example is given by showing code, and this is just a sample because the 64-bit would be just too complex. So we have 3 devices with 3 different codes, and as the devices communicate the code, okay, you can see a 1 versus a 0 is a reverse of this signal. So the idea is that you can put a lot of devices, you can still have a nice throughput of how much data you can send across, but there is encryption already implied, and then the hopping between frequencies also makes it difficult to track the signal, which is why military used this for a long time, and they still reserve the lower frequencies for multiple reasons, some having to do with lower frequencies being able to travel, say underwater and so forth, better, and also the frequency hopping would be faster on lower frequencies. Yeah. All right, so that takes us to a comparison of those, and the comparison of those is actually all, in your textbook as well. As we talk about these multiplexing techniques, which ones do you think have best chances of surviving in the future? Which ones do you think have the brightest future in technology? Wavelength? Okay, yeah, because of which properties of it? The speed, yeah. Now, in terms of wireless, right, we still have to figure out how to do wavelength well through the air. Now, if that's, if it means using wavelength just in rooms, which could be extremely fast, but yeah, I think wavelength, because of the capacity of the speed, it makes pretty good sense. Any other ones you can think of? Do you think that we're going to see more network devices in the future or fewer? Right, with iPad 3, right? I mean, there's going to be more. So code division probably has a bright future too, because we need to have technology that scales. So with multiplexing that involves time, the more devices you add, okay, the more devices you add, basically you're going to slow down the communication. And you can see that even in local area networks where we add more and more computers, and it creates all kinds of overhead. So there's scalability issues connected with that. With time division. So when basically when you have to consider the infrastructure that's included with patch cables and so forth. You have certain limitations to how many devices you can add. But with the code division, you end up issuing more addresses, and you can include more devices on the network that way. Okay, so that's our discussion on multiplexing. At this point, what I want to do is let's take about 5 to 10 minutes of break/lab, and what I'd like to ask you to do is, and you can research this on any website that you would like. But I'd like you to look for multiplexing devices that perhaps are part of our everyday life. So we can talk about SONET and networks that you've never experienced. So how about multiplexing devices that perhaps you're familiar, you just didn't realize that they were multiplexing devices. So let's give that a try for another 5 to 10 minutes, and after that we'll talk about compression.
So multiplexing device.
All right. So in your research, what devices did you come up with? Anybody with a multiplexing device that maybe is used for cooking, or sounds like one would fit in? Any devices that you think could fit the multiplexing idea? Go ahead. Radio? Okay, great. Yeah. So just like the frequency multiplexing, frequency division involves various frequencies. When you have to tune in on the radio, that's a multiplexing activity on that end. Yeah. Any other ones? Okay, TV. Excellent. So that goes both for analog or digital. Yeah. Any other ones? Okay. So you caught me by surprise here. Now, how is Bluetooth doing that?
What it does is it divides it has a little spectrum of bandwidth,
Mm-hmm.
and pair bonds with your device, and carves up that little space of frequency.
Okay. Okay, that's cool. Yeah. Very, very nice. Yeah. No, not infrared. No, that way you can walk. So infrared would require that you have visible, like a remote control. You have to have line of sight. With Bluetooth, they can walk behind a wall and it'll still work. I know because I have my car radio Bluetooth to my phone, and I no longer have to look for where I put my phone in the car. Yeah. Any other ones? You can think of even a network switch, see, doing multiplexing for the packet switching. We already discussed the DSL modem, right? So you probably have a modem device at home as well. So if you think about it, there's quite a few devices that use that kind of technology. So whenever you have multiple things coming into a central system and then one wire comes out, that is going to imply some form of multiplexing. Okay, so multiplexing, we have the train going between two devices, and the train moves at certain speed, and on the train you can load data. You can load it by saying, okay, everybody has their own cart, every third one is mine, or you can say, hey, we're going to dedicated tracks, and that's what we do with frequency. So here is the wire, and in the wire we have dedicated tracks. So multiple ways of doing that, and it works really nicely. So let's move to our next part, which is compression. now that we have the train going at a certain rate, and we put a lot of work to making sure that it's very efficient, another way to put more data through the same pipe, the same medium, would be to compress it. Okay? I think the best way to think about compression, or what happens to data when it's compressed, think about the Star Wars movie where they end up in the garbage disposal and the walls are coming onto them. You know, that's what I think when I think of data when it gets compressed. So the actual methods of compressing data are all about algorithms. Here is a great example of a simple algorithm. The data, as it sits on our train right now, are all the zeros and ones. Okay, and so this is the data. Well, why move all those zeros and ones on our train if perhaps we can put more meaning into it? And you put that more meaning by calculating how many zeros there are. And the first set of zeros, there are 14 of them. Then there's a 1, so we create a new sequence. Then there are 9 zeros, followed by 2 ones, which is represented by a 0. Then we have 20 zeros, and then a single 1 and 30 zeros. So you can see how from a long data set, we now are able to shorten the amount of data we have to put on the train. So it's not that the train is going any faster. The multiplexing techniques allow us a certain speed, and that's great. And then the physical properties of the medium. But now what we're saying is that we can manipulate the data itself, and we can squeeze it down. And when you do that, then to the end user, it'll seem like you're speeding up the connection. Okay, which is really neat. This type of compression is just an idea of one algorithm, a very simplistic approach. Because depending on what kind of data you are compressing, let's say you have an image. And when you compress an image, you can look for white spaces and simply say there is 40 columns and 20 rows of white space. Okay? So the image algorithms are going to be different than maybe compression for sound or compression for regular files like our text files and so forth. So as we talk about compression, there are two main types of compression. There's the lossless compression and then lossy. Lossless means that when you compress a file, let's say it's a Word document, you compress this file, you have a high level of confidence that it's the same file that will come out when you decompress it, that you will not lose 5 pages from it just by compressing it. So that's lossless. Lossless compression is used on your browser. When you type in www.google.com, your browser in its header, it's going to say, I support deflate. And deflate is the type of an algorithm. So then the server is going to say, okay, before I send you the page, I'm going to compress it for you. So it's turned into a zip file. We compress it, send it over network compressed, and then your browser decompresses it. See, so that way, the same internet connection, it'll look like it's faster. The bad part about compression, the downside of it, is that it requires CPU to do and undo. So what you see the server having to do is, here's my HTML file, and this HTML file has a lot of empty spaces and it has text. So when you zip it, it is a great improvement in size and fewer zeros and ones. But it takes CPU to do that. And then the browser on the other end has to work a little bit harder to decompress first and then render the page. Still, that's much faster than if you had to send the entire file over the network. Okay? So the lossless compression is used during network intended compression or when we compress data. In some file systems, so if you install Windows and you have NTFS, or if you install other operating systems with other formats, they might have compression already enabled on your C drive, you can go to Properties and you can say Enable Compression. So instead of storing a Word file with empty spots and sequences of zeros, basically the way they're stored on your computer is already zipped, which means that you can actually store more data. But it also means that when you call for that file, the computer is going to have to take a little bit of time to decompress it and make it visible to the application in the form that it understands. Okay, so some of the formats of compression, let's see. Some of the formats of compression would include, listed right here, include the Lampel-Ziff compression type and the deflate. Deflate is the most popular. Deflate. You know it as the zip format. If you use gzip on Unix, then that's what it is. Deflate is also used with the PNG, okay, the PNG extension, which is a very effective way of compressing images. In a minute, I'll show you some of the differences in using different algorithms. But look at the comment made on bzip2. It says it provides slower but higher compression than deflate. Right? So bzip2, which we use on Linux quite often, if you have a large file like a gigabyte file a gigabyte file, any increase of compression is going to have a huge, difference in the actual file space. So you will see the bzip2 used quite often, especially maybe on downloadable software, if you're compressing source files or other large sets of files. And Lampel-Ziff has gotten some upgrades since '78. If you still remember the GIF files, we used to have like multiple ones put into an animation, like animated GIF. So that's sort of the older compression mechanism. And when you looked at them, they were choppy. They were not intended for an image quality, but the size was wonderful. Very, very small. So let's look at an example here. Let me bring up maybe see what we have here in terms of pictures. There's some. Okay, so here's a picture, and I'm just going to take a screenshot of this, and I'll go ahead and create a new file with Paint. I'll paste this in, and now I'll go ahead and save this as a bitmap. Okay, and a bitmap is basically BMP. A bitmap, it's a raster-based picture, which means that every pixel is saved in the file. So that's the most basic way of saving a picture. You can edit this picture to a great detail. The downside is the size of it, right? So if I was to look at the size of my bitmap in pictures here, let's look at details. So my bitmap, and let me get rid of the other ones so that they are not confusing. My bitmap is about 3 megabytes. Now, it's hard to imagine a 3 megabyte picture on the web page, right? Because it would just take so long to download it. So what we've seen on web pages is the use of the Jpeg algorithm. And when I save it, notice that to our naked eye, there's no difference in the quality, right? Just to the naked eye. If I was to zoom it in, we would see some pixelation taking place. Because the whole idea of this algorithm is that it takes repeated spaces, like this white space here, and it basically says the next so many rows of pixels, the next so many columns are all the same color. But then when it comes to transitions between colors, it is all going to change. It basically looks different. But the result is that when you look at the size, so when you look at the size, okay, so we went from 3 megabytes to about 300 kilobytes. right? Visibly, to our naked eye, which can be easily tricked, it's the same. Which is why on the internet you will see JPEGs instead of bitmaps. But as we go forward, you see there are some great improvements made to these algorithms. So let's now try the PNG, which is sort of the current state-of-the-art algorithm. We'll save that. Again, going from bitmap to PNG, no visible change. And let's see. So it is higher than the JPEG. But the good news is that the PNG actually has a higher quality than the JPEG, right? So we cut the size in about just about 30%. But the gain, of course, is that if you were to resize it, it'll resize much nicer. There's going to be fewer pixelation issues on that. And as we view it, if this is the bitmap, I can see the pixelation taking place at a certain rate. If I was to view this on the JPEG, the expectation is that this is actually pixelated higher. Now again, without moving this bar to the exactly same size, it's going to be all more of an art. But the PNG is supposed to be fairly high quality, and that's sort of the choice for Web 2.0 and the new design. So when we talk about pictures, notice the big difference in how compression takes place on the web. As a web designer, you are expected to compress the pictures and have them compressed on the server so that when the browser requests a web page, you will already download those pictures compressed. Whereas the server is happy to compress your JavaScript, your HTML files, and then the browser will decompress them on the fly. Okay? We're not there yet to say place the bitmaps on the server and then the server is going to go ahead and compress it for you. Right? So as a web designer, you want to make sure that these resources would be already compressed. Having said that, there are technologies out there which will optimize JavaScript and HTML for high-speed network delivery. And what they will do with the JavaScript, for example, is they'll remove all the empty spaces, which are, in a JavaScript, it doesn't matter how many empty spaces you put in. It does matter to the network connectivity, because those are still zeros and ones that have to go across the wire. So all the spaces are removed from JavaScript, and it's basically just one line. All the new lines, everything is removed. It's just the one line of text. Very, very difficult to work with, right? Like visually, you don't know where everything ends. But it's optimized for network transmission. Okay, so that's our quick run through some of the compression. The one last thing I want to do is go to send to compressed zip file, and notice the compression that we get with the deflate mechanism. It's actually higher than PNG. And what's the big difference? What's the big difference between the JPEG and the PNG and then zip? How is zip different than the previous ones? You have to uncompress it to view it, yep. And what else is? Exactly. So when we did zip, we lost no data at all. So we can recreate the entire bitmap pixel by pixel. The bad part about zip is that it requires more CPU, so it's not yet, it's not accepted as a standard to basically send with zip files and then unzip them on the computer. We may get there, we may get there. The issues, of course, are, it's not that your workstation is not fast enough. It's the phones and some of the smaller devices that will choke on some of that calculations if we turn it to be that way. Because currently the browser, you see, even on the phone, it can tell the server, yes, I support compression, or no, I do not. And if you do not support compression, then the HTML, the JavaScript will be sent in text format, which again takes longer, but requires less CPU. All right, so those are some great ideas for compression. And this lossless compression applies to files, applies to network communication, places where we cannot afford losing any bit. Lossy compression applies to pictures, video, music, where our eyes can be fooled. Therefore, the technology will do that. They will send the minimum required to still make it look okay. You can maybe recall Netflix, where the first few seconds of the transmission is very pixelated, okay, because they're still negotiating the speed, maybe negotiating the encryption levels. And so the easiest thing to do is to lose some data immediately, make sure that the sound comes in okay, that the pictures are moving with the video, but the quality of them is poor because we're losing a lot of, or choosing not to send a lot of the bits that originally are in that file. So lossy. So it's okay to lose some data when we talk about the video, when we talk about pictures. Very good. All right. So today we talked about multiplexing that helps us to share media, just like we're sharing the road, right? We're sharing it. There's some rules, and we can connect to a main road from smaller ones, so we do not have dedicated driveways to everywhere you go. That's multiplexing. Compression allows us then to squeeze the data so that more meaning can be put into fewer bits. More meaning means compression, but it also means having to unzip, having to decompress the files, therefore an overhead of CPU, which on mobile devices is always an issue. So that prepares us then for discussion for next week, because next week in Chapter 6 we'll talk about error control and error detection. You see, once you are sending the bits and they're so optimized, you know, years and years people have been trying to figure out great algorithms for compression. Now that they're being sent across, now no data can be lost. So we'll talk about how you can recall certain data, how you can verify that data arrived in the proper sequence and that all the data is received. Very good. Any questions about multiplexing and compression? All right, good deal. So what we can do at this point,